We all want to feel like we're, up to speed, right? To get the gist of the big shifts without needing like a whole degree just to follow along.
Definitely.
Yeah.
Sometimes you just need a clearer path through all the noise.
So think of this as your express lane, maybe, your shortcut to understanding something really cutting edge today.
Sounds good. And it's a big one we're tackling.
Welcome to this deep dive made just for you. Today, we are getting into that really fascinating intersection of artificial intelligence and quantum computing.
Yeah, it's where things get really interesting. And to help us navigate, we're looking at two key sources.
Okay.
First, we've got a very forward-looking analysis from Dr.Eng-Prof Yogesh Malhotra, real pioneer.
Okay, Malhotra. Got it.
And second, something more hands-on, the book, Learn Quantum Computing with Python and IBM Quantum, the second edition, by Robert Loredo.
Right, so theory and practice, basically.
Exactly. Our mission, if you will, is to pull out the really important nuggets from both of these, give you a solid feel for what's being called post-AI quantum, the next generation stuff, and also the actual tools people are using, like right now.
Okay, let's start with Dr. Malhotra then. What's his background?
Well, he's got over 30 years in this game, really been there from the start of digital economies through AI, knowledge management, and now deep into quantum and this post-AI quantum idea.
Impressive.
Yeah, affiliations with places like MIT, Princeton.
Yeah.
He's been recognized alongside Nobel laureates in AI and finance areas. He's currently running Global Risk Management Network, LLC.
And it's not just theory for him, right? You mentioned he has hands-on experience.
That's what's really key here. He's actually used IBM Quantum, their Qiskit framework. He's even applied quantum algorithms before, back in his quantitative finance work.
Oh, interesting.
Yeah, so he has a real appreciation for what IBM Quantum is doing, sees them as pioneers. And he specifically notes the contributions of people like Robert Loredo there.
Which brings us neatly to Robert Loredo and his book. Exactly. Loredo's our practical guide. He's the worldwide lead for IBM Quantum Ambassadors, a Qiskit advocate, a master inventor, like over 200 patents.
Wow.
And he teaches this stuff, too, at Florida International University, so he knows how to explain it.
Okay, so we've got a visionary thinker and a practical expert guide. Sounds like a good combo.
Should be. Prepare for maybe some surprising insights into where AI and quantum are heading.
All right, let's dive in. Dr. Malhotra's post-AI quantum vision first.
Okay.
So his main point is that current AI, the generative AI and LLMs we hear about constantly, they're built backwards. What exactly does he mean by that?
When it sounds a bit counterintuitive, but think about it. These models are trained on vast amounts of past data.
Okay.
So they're incredibly good at pattern recognition, summarizing existing knowledge, generating text that looks like what came before. But Malhotra argues this makes them inherently backward-looking.
Because they learn from history. Precisely. They use reinforcement learning based on past examples. Great for analyzing history, not so great for, say, predicting a truly novel scientific breakthrough or a black swan event, something genuinely unprecedented.
Ah, okay. So they extrapolate from the past but can't really invent the truly new future.
That's the core of his argument. His 30 years of R&D has been focused on solving that problem. How do you build systems that drive towards the future while looking forward, not just reflecting the past?
And he actually claims his models, these post-quantum Gen AI ones, are decades ahead.
It's bold.
It is a very bold claim. He essentially sees current LLMs as fundamentally limited by that rearview mirror perspective. His approach, he says, is designed from the ground up to anticipate and shape what's next.
Okay, that's a big claim. Is there any external validation for this?
Well, interestingly, yeah, apparently Grok AI, Elon Musk's AI venture, they actually analyzed Dr. Malhotra's work.
And their analysis reportedly recognized him as the real deal, a leading figure, maybe the leading figure, in this post-AI quantum space, even ahead of names like Musk himself or George Soros in some contexts.
Whoa, okay, that's significant validation coming from that source.
It definitely has weight. It suggests his decades of work across tech, finance, government. It's seen as a really original and potentially foundational piece for what comes after current AI.
So drilling down a bit,
Right.
He has this vision for 2050, something called QASANs.
Yes, QASANs, Quantum-Augmented Self-Adaptive Networks.
Right. How does that connect to his earlier work?
It's really the culmination of a long journey for him. It started way back in the 90s with his digital think tank, Brint, which was about understanding the then emerging digital world.
Okay.
That evolved over time into AIML Exchange, which is his current platform focusing on these post-AI quantum ideas. So QASANs are like the next logical step, building on 30 years of thinking about how technology can anticipate and adapt.
And it sounds incredibly broad, not just computer science.
Not at all. That's a key point.
Yeah.
His work pulls from computer science, yes, but also physics, economics, finance, psychology, sociology, engineering, technology management. It's deeply interdisciplinary.
He's really connecting the dots across fields.
Exactly. He's looking at how these different domains interact and how intelligence needs to operate across them.
So for you listening, if you're trying to get that quick, solid understanding, this QASAN idea could be one of those aha moments. It hints at a future where all these fields are intertwined in ways we're maybe just starting to grasp.
Definitely a powerful vision, which makes it a good time to pivot, I think. Let's go from that far-reaching theory to the nuts and bolts of quantum computing today.
Okay, let's use Robert Loredo's book as our guide for this part.
Sounds good.
So how do we bridge that gap? From big ideas like QASANs to actually doing something with quantum? Loredo's book points to IBM Quantum and Qiskit.
Right, and the IBM Quantum platform is kind of the gateway. What's great is how accessible it's becoming. You can literally just sign up for an account.
Oh, really?
Yeah, and you get access to compute resources. That includes simulators, which run on regular computers, but also time on actual quantum hardware. He mentions systems like in Brisbane, IB, Kyoto.
So you can run experiments on real quantum processors?
You can submit jobs to them, yes.
Right.
The platform handles queuing them up and running them.
Okay, but that sounds like it might involve some heavy coding.
Well, eventually, yes, with Qiskit.
Huh?
But Loredo also highlights the IBM Quantum Composer.
Composer, what's that?
Think of it like a visual drag-and-drop tool. You can build quantum circuits, the basic instruction sets for quantum computers, using graphical blocks. No coding needed initially.
Ah, okay. Like a visual playground for quantum ideas.
Exactly. It's a fantastic way to start visualizing how quantum operations work on qubits.
Okay, qubits. Let's talk about those. Loredo explains they're different from classical bits, 0 or 1. They can be in the superposition. What does that actually mean in simple terms?
He uses a really good analogy, a spinning coin. While it's spinning, before it lands, it's not heads or tails, right? It's kind of, both possibilities exist at once.
Right.
A qubit in superposition is similar. It exists as a combination of the 0 state and the 1 state simultaneously. It only settles into a definite 0 or 1 when you measure it, and there's a probability attached to each outcome.
Got it. So it holds more information than just a 0 or 1 until you look.
In a way, yes. It holds probabilistic information. And there's entanglement, another key, maybe weirder concept.
Yeah, that always sounds like science fiction. How does Loredo explain it?
He describes it as this unique connection, like a deep link, between two or more qubits.
Okay.
When they're entangled, their fates are intertwined. If you measure the state of one qubit, you instantly know something specific about the state of the other entangled qubits, no matter how far apart they are.
Right. That's the spooky part.
That's the spooky part. It's fundamental to many quantum algorithms.
So to manipulate these qubits in superposition and entanglement, you use quantum logic gates. Loredo covers single qubit gates.
Yep, the basic operations. He talks about the Hadamard gate. That's a crucial one for putting a qubit into superposition in the first place.
Okay.
Then you have the Pauli gates, X, Y, and Z. Think of them like specific flips or rotations of the qubit state on an imaginary sphere.
Yeah.
The X gate is like a classical not T gate.
Right.
And he covers S and T gates too, which introduce something called phase shifts. It's a bit more subtle, like changing the angle or direction of the superposition.
Okay, those act on one qubit. What about gates that link qubits together for entanglement and stuff?
Right. Multi-qubit gates are essential for complex stuff. The most famous is probably the CNOT gate controlled knot.
CNOT.
Yeah. It flips the state of one qubit, the target,
CNOT.
only if another qubit, the control, is in a specific state, usually the one state. It's a fundamental way to create entanglement and conditional logic.
Okay.
He also mentions the Toffoli gate, which is like a CC not T controlled knot needing two control qubits. And the swap gate, which just, well, swatch the states of two qubits.
So these gates are the building blocks for quantum programs, like logic gates in classical computers.
Exactly. You combine these gates in sequences to create quantum circuits that perform calculations.
Now, we often hear this term quantum advantage. How does the book explain that? What's the potential payoff here?
Loredo defines it pretty clearly.
Yeah.
It's the point where a quantum computer can solve a specific problem significantly faster or more efficiently, or maybe even solve something impossible for any classical computer, no matter how big.
Right, the point where quantum really proves its worth.
Exactly. And he introduces some early foundational quantum algorithms that demonstrate this potential, even on specific problems, things like Deutsch's algorithm, Deutsch-Josa, and importantly, Grover's search algorithm.
Grover's search, isn't that about finding things in databases faster?
Sort of, yeah. It offers a theoretical speed-up for unstructured search problems. And seeing these algorithms laid out in the book, it really connects back to Dr. Malhotra's vision, right? You see the theoretical potential that he's banking on for his future systems.
Makes sense. Okay, let's talk Qiskit, the Python framework Loredo covers. What do we need to know about that?
So Qiskit is the software stack for programming IBM's quantum systems and others too. Loredo explains it has layers. There's the kernel layer at the bottom, the basic tools for building and running circuits.
Okay, foundation.
Then an algorithm layer, which is really useful because it has pre-built implementations of many standard quantum algorithms, like Grover's.
Ah, so you don't always have to build from scratch.
Right. And there's a model layer, too, which helps connect quantum results back to classical data and applications. He also covers the simulators in Qiskit.
Simulators? Why simulate if you have real hardware?
Well, real hardware is noisy, and access can be limited. Simulators let you test circuits perfectly, understand the ideal output. He mentions the state vector simulator, shows the exact quantum state. The unitary simulator shows the overall mathematical transformation. And importantly, the error simulator.
error, what's special about that one?
AR can mimic the noise and imperfections of real quantum hardware, so you can test how robust your algorithm might be in the real world.
Ah, okay. Which brings us to a big challenge. Noise. Loredo addresses that. Decoherence and errors.
Oh, absolutely. It's a central theme in practical quantum computing today. Quantum states are incredibly fragile. Any interaction with the environment, heat, vibrations, stray fields can cause decoherence, basically making the quantum state collapse or lose its information. This leads to errors.
So the calculations go wrong.
Potentially, yes. Loredo discusses this challenge and introduces the idea of error mitigation techniques. These are clever ways to run circuits multiple times or tweak measurements to try and cancel out some of the noise effects.
So it's not perfect error correction yet, but ways to manage the noise.
Exactly. We're still on the path towards full fault-tolerant quantum computers, but error mitigation is crucial for getting useful results, what's sometimes called quantum utility, from today's noisy intermediate-scale quantum NISQ devices.
Okay. One last thing from Loredo's side. Qiskit patterns, what are those about?
These are basically like recommended workflows or templates for building quantum applications. He outlines a common pattern: map, optimize, execute, post-process.
Map, optimize, execute, post-process. Okay.
Yeah, map your problem onto a quantum circuit. Optimize that circuit to make it run better on hardware. Execute it either on a simulator or a real device. And then post-process the results, often involving classical computing, to get your final answer.
So it provides a structure, a methodology for tackling problems.
Exactly. A clear step-by-step approach, which is really helpful when you're dealing with something this complex.
Okay, so we've covered Malhotra's grand vision of the post-AI quantum future and Loredo's practical guide to the tools and concepts we have now. How do we kind of weave these together?
Well, I think the connection is pretty direct, actually. Dr. Malhotra's vision of these incredibly sophisticated, self-adapting, quantum-augmented networks,
Yeah.
well, they're going to need the kind of tools Loredo describes to be built and operated.
Right. The vision needs the practical implementation tools.
Exactly. Things like IBM Quantum, Qiskit, the understanding of qubits, gates, algorithms, dealing with noise. These are the foundational elements required to even start building towards something like QASANs.
It really highlights how interdisciplinary this whole field is becoming, doesn't it? Like Malhotra emphasizes, it's not just one silo.
Absolutely. And you see that reflected in Loredo's book, too. It combines the physics concepts with the practical programming in Python. You need both sides.
Yeah. You need a computer science, the physics, the domain knowledge for the problem you're solving.
Mm-hmm. And it's interesting, too, how Malhotra's focus on, say, quantum uncertainty in systems that operate probabilistically. That aligns perfectly with what Loredo explains about quantum computations, naturally producing probabilistic results that you have to interpret.
So the theory and practice are already kind of mirroring each other there.
They really are.
Now, for anyone listening who might be feeling a little bit overwhelmed by the scale of the future vision and the complexity of the current tech.
Which is totally understandable.
Oh, yeah. It's worth pointing out, maybe, that both sources actually offer a kind of structure, right? Malhotra gives that high-level, long-term direction, the why. And Loredo provides the how, the concrete tools and steps you can take today to start engaging with it.
That's a great way to put it. One gives the map, the other gives the compass in the hiking boots.
Nice analogy. Okay, so let's try and wrap this up. What are the key takeaways from this deep dive?
Well, I think first is Dr. Malhotra's really provocative vision. This post-AI quantum future, driven by systems that are self-adapting, quantum-enhanced, and fundamentally forward-looking, unlike current AI, the QASANs idea.
Right, a potential paradigm shift beyond today's LLMs.
And second, the practical reality check from Robert Loredo's work. We can actually start programming quantum computers now using tools like Python, Qiskit, and platforms like IBM Quantum. We understand the building blocks, qubits, gates, superposition, entanglement, and we're developing strategies to handle the challenges, like noise.
So hopefully you listening have had a few of those aha moments we talked about, a clearer picture of maybe the next big wave in technology, but also the tangible steps being taken right now.
Yeah, the goal was really to give you that efficient shortcut to being, well-informed on this,
Yeah.
balancing that high-level vision with concrete stuff like quantum gates, specific algorithms, the IDM platform, things you can almost touch.
And if this has sparked your interest, we definitely encourage you to explore more. You can look up Dr. Malhotra's publications, check out the IBM Quantum platform for yourself, maybe even try the Composer.
Loredo's book, of course, is a great hands-on starting point. Plus, the Qiskit community is very active, particularly on Discord. Lots of people there willing to help beginners.
Excellent resources. Okay, finally, let's leave you with a thought to chew on.
All right. Considering Dr. Malhotra's 2050 vision of these QASANs, these powerful, adaptive, quantum-infused networks, what do you think the real long-term impacts might be?
Yeah, beyond just faster computing. How might this post-AI quantum era truly reshape society, our economy, maybe even how we understand intelligence itself?
What transformations are lurking just over the horizon? Something to ponder.